Good morning, everyone. So thank you very much, Boton, for the kind introduction, and thank you to the organizers, both the local and scientific committee for putting up such a nice event. So it's really a pleasure to be here today. And I've been to many BNP meetings since the one in Moncalieri, and it has been always a pleasure. And so it means really a lot to me to be here. And I'm particularly happy also to present this because this was motivated actually by a talk by Sergios in Oxford at the BNP 12. So today I'll talk about heavy tail priors for adaptation in general, and this is joint work with Sergios, with my PhD student Paul Egels at Sorbonne, and more recently also with Julien at Grenoble. All right, so I'll present the method first, trying to give an intuition about this generic adaptation method, and we'll delve into two different types of priors, both series priors and then deep neural network priors. And if I have time, I'll talk a little bit about work in progress now on intermediate tails. Okay, so just a very classical problem. We have a function to estimate. So think about your favorite nonparametric model. Let's be regression, inverse problems, or like a prototypical one, like Gaussian white noise, just a signal plus noise. You have also many other settings like density estimation, classification. And in all these settings, we know that the min-max rate takes this form. You have a sample size of n, then you have a power of 1 over n, beta over 2 beta plus d, where d is n-band dimension. So in the first part of the talk, for simplicity, I'll focus on the case where d equals 1. Just a traditional slide to fix notation. So prior, the model is the x given f, and the posterior is the distribution of f given x. So x given f is the model, and the reverse one is the posterior. And we say that we have a contraction rate for the posterior if the posterior puts most of its mass in a ball centered at the true. We assume that there is a true f naught. So we make frequentist analysis of the Bayesian posterior. And the posterior has to put its mass in a ball of radius epsilon and around f asymptotically. Okay, so here we're going to be interested in priors on coefficients in a broad sense. So it's a kind of an umbrella that contains both like as very classically, we can model a function in a more discrete, not by all its values at continuous points, but as just a discrete collection of coefficients in a basis. So that's the first type of prior I'll consider, so called series priors. And the second type will be neural network priors, where we put priors on the coefficients of the networks. Okay, so we don't have a basis, we have a certain expansion where we put priors on coefficients. Okay, so for the first part of the talk, we'll focus on series prior. So then the question is, what type of prior do we put on Fk? Okay, so there are many possibilities, and classical one is, let's recall what happens in the case where Fk is just Gaussian. Okay, and we then try to depart from it and see, why and what can it bring us? Okay. In the Gaussian case, if you put priors, like for instance, independent Gaussian priors on coefficients with scalings that decay polynomially, so with this decay that depends on alpha, then you can think, for instance, of Brownian motion or something like this, where alpha would be a half. Then you can prove that the posterior contraction rate is of this form. So you don't recover so here in dimension 1. So the target power is beta over 1 plus 2 beta. So you only recover it if alpha, that you can interpret sort of as a regularity of your prior, matches the one of the true. So beta is the regularity of the unknown function. Okay. So you get some rate, but the optimal rate only essentially if and only if alpha is equal to beta. Okay. And So this shows that Gaussian processes in themselves are not flexible enough to reach to get adaptation to smoothness. Okay, and so adaptation to smoothness is of course something very desirable. But we will focus on this type of adaptation in the first part of the talk. But you could think of other type of adapting to other things like sparsity, or we'll see later structure in your networks, to the architecture. So for now, we will focus on the smoothness adaptation. Okay, so in the Gaussian case, one way you can solve this adaptation problem, at least in simple settings, for homogeneously smooth functions, is to draw alpha at random. Okay, so which, I mean, it's very Bayesian and very natural, but computationally in complex model, it may not be straightforward to, I mean, you have to do a Gibbs or something to draw from the posterior on alpha. Okay, so now let me mention intriguing, thought-provoking formula that one could see in Oxford, so presented in the talk by Sergius back then. So Sergius was considering p exponential priors. So p is an index is the tail. So you can think, for instance, of p equals 1 is the Laplace prior. And so for p between 1 and 2, so 2 is Gaussian, he was getting this rate epsilon n for the posterior contraction of this series priors, where for coefficients you put p exponential. Okay, and so you remark that if p equals 2, you get beta over 1 plus 2 alpha. So this is what you had here. So here actually this formula is only for alpha bigger than beta. Okay, so that this term stays positive. Okay, so you can check. So if p equals 1, in the Laplace case, you get beta over 1 plus beta plus alpha. Okay, so you get actually a little bit better than in the Gaussian case, suggesting that if you make the tail heavier, if you go in the direction of heavy tails, then you seem to get a better rate, at least in this case, when alpha is bigger than beta, these rates improve. Okay. So then this prior, I mean, this work is restricted due to some log concavity assumption to p between 1 and 2. But if you look at this formula, it's very tempting to say, okay, what happens if suppose, let's imagine that I let p go to 0, or I replace p by 0, which in terms of tails would mean you go in the direction of heavy tails, okay, p exponential with p small. Then you get the beta over 1 plus 2 beta, so the optimal rate. So, okay, so there is natural intuition, which could be, okay, maybe we get sort of this optimal rate for free if we let the tail be heavier and heavier. Okay, so that's, in a sense, one motivation for our work here. And a bit more formally, I mean, this is what I was just telling you just now. But so if alpha is bigger than beta, and for p exponential priors, you get this rate. Okay, so this motivates naturally from this formula. One would like to, I mean, it's really tempting to say, okay, what happens since this work was limited for p between 1 and 2, so what happens if you take p small or even p go to 0? Okay. And so indeed, what you can note here is that this is not yet, for p fixed, this is not yet the optimal rate. Okay. And so if we imagine we do p go to 0, we would get something like this. So suppose we can do this, then we would get, at least in the case where alpha is bigger than beta, the optimal rate. And if alpha is smaller, we get sort of the undersmoothing rate. Okay. So we would still only be one-sided with adaptation. But then since you can choose alpha, the prior you can choose, you could imagine letting alpha tend to infinity in a sense, and if alpha tends to infinity, then you don't get this condition. Okay, so then you are always in the first case, and then you would get adaptation for free. And so that's exactly what we do. So what we propose is then to take, for series priors, we take f case to be heavy tail distributed. So here zeta k is some distribution with density h that has a polynomially decreasing tail. So you can think of a Cauchy distribution or any student type distribution. And then in front, you put some scalings. So you can put either these polynomially decreasing scalings, okay, or something that goes faster. And this is because of this idea of doing, letting alpha tend to infinity is to make it even smoother, because we saw before that alpha is in a sense the smoothness of the prior. So if you let alpha go even bigger, then and you have this formula here, this goes faster to 0 than this one. It's a bit faster than polynomial. And this is exactly right. So here I put a 2, but it could be something else. And actually there is a typo here. This Q should refer to this, not this one, but 3. I mean, here you can have a 1 plus delta with delta strictly positive, and then this 1 plus delta should be 3 half. So sorry about this. Okay, so we have then 2 priors. One is what we call the oversmooth heavy tail prior with H some heavy tail density like Cauchy, and this slightly faster than polynomial decrease for the scalings. And then we have the HT alpha prior, so heavy tail alpha prior will just mean traditional polynomially decaying scalings. Okay, and so that's what we propose. And is it good? And can we get also can we simulate from it as well? Okay, so can we get theory and does it also work in practice? Okay, and so before I present the result, let me give an intuition. Try to give an intuition on why this could be a good idea to have heavy tails for adaptation in general. And so for this, I'll consider maybe the simplest statistical model, so just a Gaussian n theta 1 and some prior on theta. So here there is just one observation, so extremely simple. And I just consider these 3 different priors. So either you take a Gaussian prior or a Laplace or a Cauchy one. And we'll have 2 informal goals in this little experiment we will do now. One will be that if X is big, you want to keep it because then it means that probably there was signal. And if X is not very big, then we'd like to shrink it possibly, okay? Because then we think, okay, maybe we can ignore this observation. Okay, so we would like to have these two effects. And let's see if we can achieve it with this priors, or maybe doing something extra to this prior, okay? So if we have a large signal and one of these 3 priors, so you see that as expected, if you have a Gaussian prior, the red one, it's centered at x over 2, so centered at 2. And with heavy tails, I mean, as one could expect, you are less shrinked to 0, okay? And so if x is 0, then you get this, okay? Everything is centered. And so what's not so nice here is that you don't shrink too much, okay? So the spread is still relatively big. So that motivates multiplying these priors by some scaling sigma, some small scaling, in order to be shrinked when the signal is not very large, okay? So let's see the effect of this. So if you have a Gaussian prior that you multiply by some small factor, you will be even more shrink towards 0, right? But if you have something more heavy tail, you see that, so for Laplace, you are a bit in between, but for Cauchy, you stay still, the prior still puts quite a lot of mass around 4, okay? And then you can decrease the scaling, so even smaller scaling, 0.3 now, and 0.1. Okay, and so you see that then here for 0.1 scaling, so quite small, the Laplace is shrinked quite a lot, almost like not the Gaussian even more. And here for Cauchy, you start seeing some amusing phenomenon. It starts to be bimodal, so it almost starts looking like a spike and slab. So it is a posterior, right? But it has this kind of 2 modes, one close to 0 and one closer to the observation. Okay, and if x is 0, then you have this desired scaling that is achieved by taking the small signal. Okay, So, in fact, so the one way of seeing this is that this prior, just this sigma times the Cauchy, it achieves by just having this heavy tail and with the deterministic sigma, something that is, in a sense, close in spirit to spike and slab, despite being much more, much simpler. Okay, so it's very simple, just sigma deterministic and some Cauchy. Okay. So now, after this introduction, let me go into the results. So first, for series priors, so let's consider, just to fix ideas first, the very simple white noise model, which is when you project it, you just get a signal plus noise in a Gaussian sequence. Okay, if you project this against any orthonormal basis, this is the Fourier basis, and then you want to estimate the collection of FKs. So assume that F0 is beta smooth in the Sobolev sense. And let's take the priors I was suggesting before, so heavy-tailed priors. So the first result says that you get exactly what we were hoping for. That is that you are adaptive up to a log factor. So ln in the rest of the talk will be just some log factor. You get adaptation, so the optimal rate, with this heavy-tailed prior, so with the OT prior without any condition, and for the HT alpha prior, so HT alpha, recall, is just the ones with polynomially decreasing scalings, then you get one-sided adaptation, so you get adaptation if alpha is bigger than beta, and otherwise you get the n to the power minus alpha. Okay, so this shows that this conjecture that we made before is true, and the heavy tail combined. So the idea is really so heavy tail itself is nice, but it's even better to combine it with a small scaling in front. Okay, and then you get adaptation over the whole range of smoothness. Okay, and so computationally, I'll show simulations in a second. What's nice is that then to sample from the posterior, you only need a plain MCMC, because then you can just do MCMC on the FK. So you don't need to sample from a hyperparameter posterior, like if you would do Gaussian priors and then put the prior on alpha, you would have to sample from the posterior on alpha. Here, you don't need this. Okay. So let's me show you a few examples. So you can do linear inverse problems. So a bit still in a white noise model spirit. So you project into sequence space. Then you have, if you have a linear operator, this will give you some linear multiplication by some decreasing sequence in front of your coefficients. So for instance, you can have this classical Volterra operator. And so in this case, if you take the OT prior, you again get convergence to the minimax rate and adaptation completely for free using this heavy tail ideas. And so if you take the HT alpha prior, you have something similar, but only one side. Okay, so some little experiment here. I mean, the gray is maybe not very visible, so there are some spaghetti plots here. I hope you can see them still. So the right column is our method. So the left is a Gaussian process with random alpha, so with smoothness parameter sampled at random. And the middle one is the OT prior, sorry, the HT alpha prior with the alpha that is quite mid-specified. So here we take a prior with a very fast decay, alpha equals 5, whereas the true smoothness is just 1. But we see that still, I mean, even though the uncertainty quantification is not so good here because it's quite narrow, but you still see that asymptotically you are still quite good in catching you still achieve adaptation in terms of the pointwise, in terms of the point of symmetry. But so what we recommend is the OT prior, and you see that it performs at least as well, even maybe slightly better than the Gaussian plus random rescale. And we'll see that actually you do get better than the Gaussian in the sense that you you can be adaptive to more inhomogeneous smoothnesses also, if you want. Let me come back to it in a second. So I don't want to enter too much into the details, but you can to technical details, but you can generalize this to so if you have instead of the Fourier basis, you have you can take any basis. So in particular, you can take a wavelet basis. So then generally we have the double index notation, and then consider more general spaces than Sobolev spaces. So the idea behind these other spaces, which are more complicated definitions, so this is a base of ball, is that you can model more complex smoothnesses, like inhomogeneous smoothnesses. And then the natural question is to ask whether also this heavy-tailed prior, they can also get optimal rates for these spaces. And the answer is actually yes. So in the first paper with Segios, we showed that for base of spaces of this type, so where you have this indices matched. Recently, we also considered the general base of spaces, so B, P, Q, beta, and the general losses with my student Paul also and Segios. So I don't give the details here, but we have a preprint on arXiv if you are interested. And so this work shows that you can also get a minimax rate over essentially any type of base of spaces with possibly a non-matched norms. We also computationally, it performs, it's competitive, it performs as well as state-of-the-art wavelet packages, where actually in these wavelet packages, they have to tune even the kind of the thresholding coefficients. So those are thresholding methods where they really tune the thresholding constants. Here we didn't tune anything. We just took this OT decrease with this log to the power of 3/2. Okay, so you can do you can depart from. So for now, for simplicity, we focused on the white noise model, so signal plus noise. But you can depart from that, and then technically. At the moment, we don't know how to apply the generic theory by Art Subhashis. So in that setting, because of the heavy-tailed prior, so it's quite challenging because of concentration, because you don't have like Gaussian or Laplace concentration. So then we can resort to looking into row posteriors. So row posteriors is the generalization where you put the likelihood to a certain power rho. And technically, it's easier to work with this because you only need to control prior mass to get row posterior contraction. Okay, but so if you are willing to work with this prior, I mean, if you can comment on that more if you're interested, but then you can essentially obtain results also for many other models, much beyond, say, simple Gaussian white noise. So, for instance, density estimation. So if you put your series prior in exponential and renormalize, then you get, again, adaptation. So sampling is done, as I mentioned already briefly, by doing some whitened PCN and no Gibbs, because you don't have hyperparameter to sample. So here is a little picture in density estimation, where on the right, we have our method, so the OT prior. On the left, we have GP Gaussian process exponentiated and renormalized with a misspecified smoothness, alpha equals 5. So as you see, I mean, as expected, it doesn't perform well because the smoothness is misspecified, and we have seen that GPs are you know, you have to specify well the smoothness parameter to be optimal or close to optimal. And this in the middle, you have the HT alpha prior, where again, misspecified alpha. So you see that you, even though alpha is misspecified, you perform already much better than the misspecified Gaussian. Okay, so we can also do classification. Maybe I'll be quick on this one. It's again a quite similar picture. So here the goal is to estimate the classification function. You can be fully adaptive with up to log factor with the OT. and one-sided adaptive with the HT alpha. You can do nonlinear inverse problems. So here I'm advertising Sergio's talk if you're interested tomorrow. So it's we can work, for instance, in a nonparametric regression style inverse problem where GF is some nonlinear operator, and under some conditions on GF you can get contraction rates for row posteriors. And here are some simulations in that setting. So please, if you are interested for more details, please go and see Sergio's talk tomorrow. Okay, so let me now delve into the second type of class of priors, so deep neural networks. So can we use these ideas also to in the setting of deep neural networks? So by putting certain priors on the network weights. And so one of the motivations of this study was that if you look into the theory for deep neural networks, so all results I know, I mean, they are very, in simple settings, they are now nice results. I mean, for feed-forward neural networks, we have nice oracle results. I mean, oracle in the sense that if you know the architecture, so in particular, if you know what is the width you want to take for the network and the depth, then you can show that a network with this architecture, so for instance, if you do empirical risk minimization, then you get the optimal rate for certain non-parametric classes. Okay, so that's nice, but in most results I know, you are really, you must choose the architecture well. In particular, for instance, the width. If you take a logarithmic depth, you need to choose the width well. And we don't kind of explain what's observed in practice, that people take a large architecture. Okay, so they take a large width, maybe moderate depth, and it seems to work. Okay, but to the best of my knowledge, there is really no theory on, for instance, the ERM empirical risk minimizer in a case where you are really over-parameterized, okay? Because you have the statistical, classical statistical bias variance trade-off, and if you are too much over-specified, then we don't know what rate you get. So one motivation for this was also to ask whether we can provide some theory in a setting where we are really over-parameterized. Of course, there will be some sort of penalty and that will come in the scaling, but one motivation is that it will be much closer in spirit, at least, to the methods that are used in practice. Okay, so a bit more formally, we will consider ReLU a deep neural network. So rho is the activation function. So the prior here is on Fs that are defined as compositions, where so you have an X here that is multiplied first by a certain matrix and then goes into the activation, which is this ReLU here with a shift B1, and you iterate this, alternating the linear operations with the shift and then activation to get your function f. Okay, and so our goal here will be to try to make the prior as simple as possible. Okay, so what is the simplest prior? It's just to take a large width and maybe moderate depth here, so say logarithmic depth and large width, say n or square root n. You will be over-parameterized and then put some priors on the weights, okay? Maybe the simplest choice is Gaussian, okay, why not? Come back to it later. Or something else, but IID weight seems natural. And in particular, if you think of even like standard methods like gradient descent on neural networks, generally, so you can view the people train the network by initializing the weights to using, for instance, Gaussians and this large architecture. So in a sense, you can view by analogy a bit the prior a little bit like an initialization. Okay, so in this view, it seems really natural to have IID priors on weights in using a large and deterministic architecture. Okay, so the statistical model we consider here is a nonparametric regression. So one interest of neural network is that even though the minimax rate is here features a dimension d because you know that's the minimax rate in RD, but what we hope is that actually the data has some smaller dimensional structure where here you will have something maybe with D replaced by a D star, which is an effective dimension. And we hope that we have methods. And it has been shown that indeed neural networks methods satisfy this, but perhaps other methods as well, get a rate that is adaptive to this unknown structure with the intrinsic dimension here instead of the ambient dimension D. Okay, so I mean classically, for instance, in these examples, in fact everything depends only on one coordinate. So you would get a rate here much better if you knew in advance that your function depends only on one coordinate. Okay, then in fact, you know, it's kind of very simple to get this rate, but the challenge is that in advance, you don't want to make any assumptions on the structure. And so neural networks are among the methods that can get this. Okay, so the different settings were, just to be a bit more precise. So for instance, a natural setting is if your design points xi sit on a D-star dimensional manifold, then you can show under some conditions that the optimal min-max rate is indeed, as I was mentioning, something like this with D-star, the intrinsic dimension. You can do also compositional structures. So if the truth is a composition, then it can be shown that the rate has this type of form where beta primes are sort of intrinsic regularities and TIs are intrinsic dimensions in the different layers of the composition here. Okay, so I mean the exact expression, I don't have to get into the details. The idea is just that you have some form of intrinsic dimension and smoothness that replace the traditional one. So if your data in fact has structure, then you get better rates. Okay, and the challenge is building methods that get these rates without assuming in advance that, for instance, you know the manifold or you know that your data is sitting on a manifold. Okay. So just to mention previous work on Bayesian neural networks. So for posteriors, so one option is to take spike and slab priors. Okay, so theoretically it's very nice, very natural. The problem is that computationally it's harder. So you have to, in that case, you have to do VB, something a kind of approximation, and even VB is not so simple. You have to do some approximations. You have to replace the direct mass by some modified version, and it doesn't scale in general, maybe as well as other simpler alternatives such as just Gaussian weights. Okay, so you can do model selection style priors where under some conditions you could maybe sometimes do some MCMC. So one recent proposal is to take Gaussian weights, but random architecture where you use a random width, but then you have to sample from the width. Okay, so we said that we were wanting to have the prior as simple as possible. And so maybe the most natural option is just to have, as I was saying, just independent non-zero weights. So there is work, for instance, by Jae Young on this, where you put so independent weights, but theoretically you don't have adaptation. And there is also a nice work here in JMLR where they propose a variational base for horseshoe type priors on the weights, but no theory. And so actually with what I'll present later, we didn't formally put it in the paper, but you can actually also, from our approach, you could also get theory for this type of method with horseshoe weights. Okay, so what we'll do here, really in the spirit of what I've presented before, is okay. Let's just use this very simple idea from the 1D in simple experiment that I presented before. So we just take some heavy tail like Cauchy, a prior, times some small scaling factor, some normalization. Okay, and we'll take a large width that is deterministic, and we hope to have some form of benign overparametrization, meaning that, I mean, this, for instance, if you take n as the width, it's overparametrized. Okay, and the depth will take logarithmic, and the question is, although we are overparametrizing, can we still get optimal rates and adaptive rate that depend on the effective dimensions and not on this degree of overfitting, namely on these two large widths. Okay, so the prior is now will be familiar because it's exactly what, I mean, the spirit of what we presented before. We just take slightly faster, here there is a 2 and 1 plus delta, slightly faster decrease of the sigmas. So you can take sigmas that are equal. So here, so this means that for all the weights in the neural network, so both for the matrices and the shifts, you take independent distributions that are scaling times the heavy tail distribution. Okay, so for instance, you can take a student. You could have different forms here. You could make this depend a bit on where you are in the network, but for simplicity, I mean, that's in the paper. But so that's a joint work, by the way, with Paul Egels. So if you do this, so before getting the result, you can also do VB. So if you can do mean field variational base, so then the mean field family that you take is just a product of the heavy-tailed distribution that you have taken for your prior to be the closest in spirit to your prior, but and then you are just mean field. Okay, so you can also consider this Q star, which is the best approximation to your row posterior here in the KL sense. Okay, so that I've already discussed. And so what you get, the result is that you get what you want, namely that for both the row posterior or its variational base approximation, you get an optimal rate that only depends on the effective smoothness and dimension parameters. So compared to the literature, all the, I mean, the results we know were in the frequentist literature, they are all non-adaptive. So, I mean, if you could possibly make them adaptive, but you have to do some form of cross validation or some model selection, which would be very, I mean, not so simple to do computationally. You can also do manifold data, where then you adapt to the intrinsic dimension. You can do also anisotropy in Bezoff's sense. I'll skip that. So just to summarize, what we get is that using this simple idea of having this oversmoothed or overshrinked heavy-tailed priors, and then you can just take an overfitting or overparameterized architecture, the big architecture, you get automatically adaptation to both smoothness and structure. And you can, in principle, then do both MCMC and VB. So we have not yet investigated in full the sampling aspect, but what's nice is that you don't have hyperparameters to sample from here. Okay, and maybe if I have a couple of minutes, I can maybe just 1 minute. Let me just briefly discuss a connection with heavy tails, because now, so with Gaussian tails, especially for neural networks, so they are nice results by Julien Arbel and co-authors that say that if you look at IID weights for your neural network and you look at the output here, so it's called post-activation, you get after L layers, you get a variable type distribution of index 2 over L. So you get, in a sense, even starting with Gaussian priors, after a certain number of layers, you get anyways heavier tails. Okay, so it seems that there is an interesting connection with our, what we did before was just to put heavy tail prior directly, but even starting from Gaussian, you, in a sense, get already heavier and heavier tails, and this motivates, in a sense, a study of the intermediate case where you are p exponential. So Sergius already did the case p between 1 and 2, but here we are interested in the case where p becomes small. Okay, so this is now work in progress with Sergius and Paul. We extended Sergius' formula to any p, and now we are also particularly interested in the case p goes to 0. So first in the non-parametric setting of series priors, and then for ReLU networks with p exponential weights. Okay, so let me conclude quickly now. So just to say that this method is quite general. It enables to get adaptation in a variety of settings. We are exploring it. I mean, computationally, it seems to work also very well. And now we are investigating, in particular, this. So we have investigated quite a bit the heavy-tailed, fully heavy-tailed, like Cauchy or student case, and now we are getting back to also to intermediate tails, motivated in particular by this results by Julien, and trying to make progress in that direction. Okay, thank you very much. Yeah.
So since heavy tail prior would already work well in this case, have you considered, I'm curious, have you considered, for example, specific heavy tail priors like the horseshoe in this case?
Yes, so that's a good point. Yes, so we have actually in this preprint with Sergius and Paul, we propose theory for the horseshoe in the non-parametric setting, in the series prior setting. But you could do actually you could already readily apply our results for neural network. You could apply it with the horseshoe, at least for the posterior. I mean we have a remark in the paper, but yes, you can do it. But so then you, in a sense, we still, maybe the conclusion in the preprint that we have is that maybe we still recommend the OT over the horseshoe, because the horseshoe, it also models like the spike at 0 in a sense. And here we don't model it really randomly, but just by deterministic scaling. So in a sense, it's a bit simpler, but you can do the horseshoe as well. So in a sense, maybe the horseshoe is a bit more adapted to sparsity settings, if you wish. But
yeah, so it will sense a lot. So I got 2 questions. So first, I think you mentioned like in the first part, adaptation to smoothness, you can adapt to inhomogeneous smoothness, right? So that's the first question. Maybe you can comment on that. The other question is for a neural network, you have a very specific choice for both the width and the depth. So width is square root of n and depth is power of log n. So is any kind of secrets behind this choice? Is this choice very important, or you can do other choice as well?
Yes, so for inhomogeneous smoothness, I didn't have time to comment more. Yes, so you get this result, and please see the preprint if you want more details. You can do this. And for the neural network, indeed, so it's a good question. So for the width, it doesn't matter. You could take any polynomial type smoothness. So if you take the polynomial n to the a and a is too small, it doesn't matter. You get adaptation just in one range. So the rationale between for taking the square root n or the n is that it guarantees you full adaptation, and you could take something bigger if you wish as well, and squared would work as well. Yes, and the depth, we only investigated logarithmic depth. In principle, you could still hope that you can do something very general, but we didn't look into it.